Hi everyone, I'm John from Prodaic Labs and this is session number 1, Introduction to FEA. This video session will teach you all about FEA, its meaning and how does it work. So let's get started. After completing this session, you'll be able to understand what's FEA, what areas can FEA be applied, and how does FEA work. So first, let's try to understand about finite element analysis. FEA can be summarized in 3 points. It's a numerical method, traditionally a branch of solid mechanics, nowadays a commonly used method for multi-physics problems. And the areas where we can apply FEA are structure analysis, for example, a cantilever, a bridge, an oil platform, and so on. Solid mechanics, a gear, an automotive powertrain, etc. Dynamics, vibrating structures or machineries, bullet impacts, etc. Thermal analysis, heat radiation of thin surface or thermal analysis or a PCB board. CFD, to understand the fluid flow pattern. Electrical analysis, piezo actuator, electrical signal propagation, etc. This is the time when we have to deep dive in FEA. FEA was originally developed to solve solid mechanics problems. Let us consider a solid object, but with known mechanical properties as shown here. This is under formed condition. Before we go further, let us define some concepts of FEA. First one is boundary. It's nothing but surface enclosing the geometry. Second is solid. It's interior plus boundary. Third is known as boundary condition. It can be defined as prescribed quantities, such as prescribed displacements and prescribed tractions on the boundary. We have a question here. What if we apply a force on this solid? What would be the values of the displacement, stress, and strain at each material point? We have some inputs in the form of boundary conditions, which have to be translated into desired outputs, and the output would be in the form of displacement, stress, and strain at each material point. So this is typical FEA problem. To answer this question, we need to solve some mathematical equations as shown here. We need to solve a problem consisting of total 15 equations, among which 9 equations are partial differential equations. Finding an exact solution is mission impossible. So, mission changes to find a solution that approximates the exact solution. And FEA is a numerical method that offers a means to find the approximate solution. Let us understand as how does FEA work. To do this, consider this integral equation. This equation basically represents area under the curve as shown here in the picture. And the exact solution works out to be 38 by 3, which is nothing but 12.667 for 3 decimal places. If we try to solve this using numerical method, we can do so by following the steps mentioned here. 1. Divide the interval of integration into n section. 2. Choose a function to approximate the variation of f, x in each section. The simplest such function is a constant function that equals to the value of fx at the midpoint of each section. 3. The product of this constant function and the length of the section approximates the integration of fx over this section. 4. Summing the products for all sections gives an approximate answer to the integration of fx over the range -1, 1. We have considered 4 different cases with a value of n from 1 to 4. As value of n increases, percentage of error decreases, which means finer mesh translates into more accurate results. Let's talk about the general procedure of FEA. As a first step, take the physical model and define the problem we are going to work on. It's basically conversion of a real-world engineering problem into an FEA problem. Next step is called pre-processing, where we define the material properties, mesh the model, and apply boundary conditions on it. Next is FEA theory, where we choose approximate functions, formulate linear equation, and solve them. This is core FEA and involves mathematics. The last step is known as post-processing, where we have to obtain, visualize, and explain the results. So that was the procedure of FEA problem.
Thanks, John, for taking time to explain core points of FEA. Now, I'll walk through some of the key assumptions of FEA. There are 4 types of assumptions in FEA that must be considered while performing any analysis. These assumptions are not comprehensive, but cover a wide variety of situations applicable to problem. First, assumptions related to geometry. Displacement's values will be small so that a linear solution is valid. Stress behavior outside the area of interest is not important. Therefore, geometric simplification in those areas do not affect outcome. Only internal fillets in the area of interest will be included in the solution. Local behavior at the corners, joints, and intersection of geometries is of primary interest. Therefore, no special modeling of these areas is required. Decorative external features are assumed to be insignificant for the stiffness and performance of the part, and these external features will be omitted from the model. Variation in the mass due to suppressed features is negligible. Second is assumptions related to material properties. Material properties will remain in the linear region, and the non-linear behavior of the material property cannot be accepted. Material properties are not affected by load rate. The component is free from surface imperfections that can produce stress concentration. All simulations will assume room temperature unless otherwise specified. The effects of relative humidity or water absorption on the material used will be neglected. No compensation will be made to account for the effect of chemicals, corrosives, wears, or other factors that may have an impact on the long-term structural integrity. And third one is assumptions related to boundary conditions. Displacements will be small so that the magnitude, orientation, and distribution of the load remain constant throughout the process of deformation. Frictional loss in the system is considered to be negligible. All interfacing components will be assumed rigid. The portion of the structure being studied is assumed as a separate part from the rest of the system, so that any reaction or input from adjacent features is neglected. And finally, we have assumptions related to fasteners. Residual stresses due to fabrication, pre-loading on bolts, welding, or other manufacturing or assembly processes will be neglected. All welds between components will be considered as ideal and continuous. The failure of fasteners will not be considered. The load on the threaded portion of the part supposed to be evenly distributed among the engaged threads.
If you have any questions, you can find us on social media. Thanks for tuning in and have a great day.